So I hope the share screen is working.
Yeah, it's working. Yeah.
Okay. So yes, hello and welcome to my talk where I revisit description logics with concrete domains and general concept inclusions. And this is joint work with Franz Baader. So concrete domains were introduced to description logics to allow for concept descriptions with predefined structure, such as age, location, or size. And here, for instance, we have a concept that describes an individual who is a human and has a parent and also a grandparent who are of the same age. And obviously, this should be unsatisfiable with respect to any reasonable knowledge base. But also, we should have some uniform understanding of how age is interpreted, and it should not depend on a T box that we're working with. So now let me present a standard inclusion of a concrete domain in the description logic ALC, which is our main point of reference. And these are like the most general concept constructors that allow us to include concrete domain in the logic. So let me just break this constructor down. So from a mathematical point of view, a concrete domain is a relational tau structure. That means a set of elements together with some relations that can be accessed to symbols from a given signature tau. And in our concept constructor here, we also have phi, which is a k-array first order tau formula, which means that, okay, the signature is the same signature as the one of the concrete domain. And now on the side of ALC, we allow for role names in this constructor, which interpret as usual roles in ALC interpretations. And then we also have something that connects ALC interpretations with the concrete domains, which are features, and they interpret as partial functions from the domain of an ALC model. So from ALC models to the domain of the concrete domain. Okay, and now instead of going through this complicated definition, let's just see this concept on a sketch. So an individual is contained in a concept of this form in an interpretation I, if it has some successors with respect to the roles Ri, and these successors, which are denoted by the first column of black dots, have some function values with respect to the partial functions Fi in the concrete domain. And now this tuple that is formed by this assignment should satisfy indeed this formula phi. So this is the general concept definition. And now concept satisfiability with respect to GCIs in ALC with the concrete domain D somehow combines reasoning in ALC with constraint satisfaction in D. So if we look at the concept from the previous slide, we can add the following. We can observe it with respect to the following GCI, which tells us that every human being has only parents who are also humans, and also the age of a human being is strictly less than the age of any of its parents. Okay, and now if we want to infer that the concept above is unsatisfiable with respect to this GCI, we first work on the level of ALC to propagate the human concept to the parents. And then we use the second part of the GCI to build a small system of constraints, which we then solve in the concrete domain D, and realize that it is unsatisfiable. Okay, so this problem is decidable, for instance, for ALC equipped with the concrete domain of rational numbers with the order relation, equality, and the reverse order relation, and this follows from a result of Lutz. But the problem can quickly become undecidable. For instance, already for ALC equipped with the concrete domain of natural numbers, the success relation, and the constant zero, we already get undecidability, and this is also a result of Lutz. Our first contribution is showing that concept satisfiability with respect to GCIs is already undecidable in ALC extended with natural numbers and a successive relation. And the idea is that in the original proof of Lutz, there was a reduction of the halting problem for two-register machines to concept satisfiability, and we were able to simulate this reduction and especially the zero tests without actually having the zero in the signature. So the natural numbers could also be changed for integers or any other number system that is infinite. Okay, but now let's look at decidable concrete domains, which are probably more interesting. So our result studied a result of Lutz and Milicic from 2007. They have shown that concept satisfiability with respect to GCIs in ALC equipped with a concrete domain D, where the concrete domain formulas, by which I mean this phi that we've seen before, where these concrete domain formulas are restricted to disjunctions of positive binary literals, is decidable if D is omega admissible. So they've isolated a sufficient condition for decidability. Okay, and now let's go through this condition. I've broken it down to 5 points, and I've also reformulated it in the language of relational structures, which is more handy for what we've been doing in our paper. So D should have a finite binary relational signature tau. We've already seen that before. Its relations should be jointly exhaustive, short JE, and pairwise disjoint, PD, which means they should somehow fill in the whole two-dimensional plane, and they should also not overlap at any point. And the constraint satisfaction problem of D should be decidable. So this is the problem that gets as an input a finite tau structure A, which means that this structure has the same signature again as the concrete domain. And the problem is to decide whether D homomorphically maps, whether A homomorphically maps to D. And many computational problems can be formulated as CSPs. For instance, satisfiability of linear equations. We can take the linear equation system and build a finite structure from it, and then satisfiability corresponds to existence of a homomorphism. Okay, so some examples for these first three conditions. We could take, again, relational numbers with order, equality, and the reverse order. And the CSP of the rationals with order is the digraph acyclicity problem, which is decidable in P. And the second example, we could take just the set of three elements with equality predicate and the inequality predicate. And the CSP of the inequality predicate on three elements is just the three colorability problem. So these are very natural problems up to now. Okay, now let's look at the fourth and the fifth conditions. They're a bit more tricky. The first is called the patchwork property, and it requires that for all finite, jointly exhaustive and pairwise disjoint tau structures A, B1, B2, such that A embeds to B1 and also to B2. And there is a homomorphism from B1 to our concrete domain and also from B2 to our concrete domain. There should exist some new homomorphisms, potentially also from B1 and B2 to D, which commute with the original embeddings. Now, to understand this in a more illustrative way, if we have two systems of constraints which are independently satisfiable in D, and they overlap on some intersection A, then they should also be consistently satisfiable. And the last condition is known as the compactness property, which requires that every time we want to test a countable tau structure B for a homomorphism to our concrete domain, we only need to check its finite substructures. Okay, so now examples for all five conditions. Both of these examples were already present in Lutz and Milicic's original paper. Allen's interval algebra with 13 relations can be used to describe relations between intervals, let's say, of rational numbers. And second example, region connection calculus can be described to describe some relations between regions in a Euclidean plane. The problem is that it is in general very difficult to verify 4 and 5 for a given D, and there are not many examples that would be known for these conditions. So what we generally did in our paper is we have shown that 4 and 5 are actually known from model theory. So we've given some different model theoretic properties that can be found in the literature, and then that can be related to the patchwork and the compactness property. But here, for time reasons, I will only give you the our main result, and also some notions that are necessary to comprehend this main result. So the first notion, a structure D is homogeneous if every isomorphism between its finite substructures extends to an automorphism. We can again look at rational numbers with order. If we take two isomorphic linear orders which sit somewhere in the rational numbers, Then we can extend this isomorphism to an automorphism by mapping the intervals in between the points through some linear transformations. So the automorphism would be a piecewise linear transformation. And we work with a slight additional assumption, that is that D is jointly diagonal, short JD, if the equality predicate can be written down as a union of relations of D. So for instance, if we already have the equality predicate in the signature, then we are fine. Okay, so what we've shown is that if D is a countable structure that is jointly diagonal, jointly exhaustive, and pairwise disjoint, the structure also has a finite signature, then the homogeneity of D implies the patchwork property and the compactness for D. So for homogeneous structures, which already cover the Allen interval algebra, the RCC, and also the rational numbers, we get patchwork property and compactness just from homogeneity. The converse direction holds up to embedding equivalence, which means that if we have a structure that satisfies the first line in this statement, then if it has the patchwork property and compactness, then we get another structure which embeds into the original, and the original also embeds into this other structure, and this new structure is homogeneous. Okay, so now to tackle the CSP, decidable to CSP, we pose a slight restriction. A structure D with a finite relational signature is finitely bounded if its finite substructures are precisely the finite modulus of some universal first order sentence phi D. So examples are again rational numbers Ln or RCC8, and in the case of rational numbers, this first order sentence will just give us all the axioms for linear orders. So a very natural definition. So what is important or interesting about this combined notion is that the first order theory of a finitely bounded homogeneous structure is always decidable in p-space. And this in particular implies that the CSP of D is decidable, because CSP can be formulated as a satisfiability of conjunctive queries. And also what we use in our paper is that every finitely bounded homogeneous relational structure is first order interdefinable with a one that is jointly diagonal, jointly exhaustive, and pairwise disjoint, which means we start with a structure finitely bounded homogeneous, and we can form one that has the same universe and has possibly different relations, but we can interdefine the relations in first order. So example, we start with rationals with the order, and we can first order interdefine it with the structure which satisfies this JD, JE, PD. Okay, and one last important property of this family is that if we look at the reducts, which means we can drop some symbols from the signature, then the class of the reducts of finitely bounded homogeneous structures is closed under expansions by finitely many constants, and also under certain specific products, which allow us to, for example, combine Ln and RCC8, and we still preserve the finite bounded homogeneity, which gives us, again, the restrictions of the CSP, of the complexity of the CSP. And our main result states that concept satisfiability with respect to GCIs in ALC with a concrete domain D, where the concrete domain formulas are arbitrary, so arbitrary D-array first order formulas. Concept satisfiability is decidable if D is finitely bounded homogeneous and it has at most D-array relations. So there is a correspondence between the arity of the relations and the arity of the formulas. Now, why we believe that this result is interesting is because finitely bounded homogeneous structures are the main object of study in the infinite domain constraint satisfaction. So we hope that there will be some results that can be lifted to concrete domains. For instance, there's an example of one recent result of Bodersky, Knoyer, and Starke, who have shown that for binary signatures, it is actually decidable whether a universal first order sentence describes a finitely bounded homogeneous structure, which means that we can start with a universal first order sentence and then check whether there is a concrete domain that can be used for a decidable reasoning. Okay. Thank you for your attention. This is all.